All right. Thank you for joining us here Saturday. Okay. So, does everybody have a deep learning booklet? If not, there's more in the back, so I think it's massive. It's basically a R video. For those who don't know what that is, don't worry, it's just a little documentation for our deep learning module in H2O. And it will go much more about this by the end of these 90 minutes. So if you want these slides, they will appear on our Next.ML website, of course, but for now you can all share them there and follow them over that. Try to make this as loud as possible. Is this okay? Yeah. Okay, perfect. So play.cc, that is your Next.ML slides with underscores in between the words. That's where you will find these slides. Our website is H2O.ai. That's where you will find all kinds of documentation. You can download the product itself, the H2O jar file, basically. It's a Java-based software. I'll wait for a few seconds until everybody has these slides downloaded, or at least pointed to a website. It's hosted on SlideShare, so it shouldn't take too much bandwidth. Okay? So my background is basically supercomputing, and the last 3 years I spent in machine learning. So I'm a half supercomputing person with 100,000 cores, and now I'm getting deeper into the math and the algorithms and doing it for enterprise customers. So it's not just about doing cool stuff, but also doing it in a way that the actual customer at the end is happy with it. So it has to work in production on a Hadoop cluster, it has to be scalable for big data. If you have a 500 gigabyte data set, you don't want it to just run out of RAM on your one machine. Stuff like that. I'm from Switzerland, as you can tell, and actually got nominated and also named one of the big data all-stars last year. That was fun. So the outline for today is pretty simple. I'll tell you what H2O is. We expanded. Everything is automatically standardized. Missing values are handled automatically. There's regularization options that you can specify. So basically, the idea is that it just works for you. You just press a button, and out comes something smart. And you have the option, of course, to tune these hyperparameters. We have about 50 hyperparameters in deep learning. That's why I think it's booklet, right? There's a lot of little tools that you can turn the knobs on yourself, but you don't have to. The idea is that it will just run on its own. All you need to know maybe is 1 or 2 concepts that will make your life easier. If you're processing 100 gigabytes, maybe you need to know something that would make this whole endeavor a little faster. So it's worth reading this booklet. But in theory, it should just work. We also have unsupervised learning, but for those of you who don't know this, I mean, is there anybody here who hasn't seen this schematic before? No, right? So deep learning is just several layers, in this case 2 hidden layers. You have, for example, I'm predict that you're married or single based on your age, income, and employment status. And we have pan-H, rectifier, and max-out activation functions that basically are used to make these predictions and generate these hidden features. And we use the softmax for classification of just regular linear output units for regression. Of course, standardization that I mentioned earlier is important. You don't want to have age and income compete because income is 100,000 and age is only 10. You need to have standardized in the same number space. And if you have categoricals like cat, dog, mouse, you want to have cat, yes, no, dog, yes, no, mouse, yes, no. But you just realize cat, dog, mouse, I only need to tell you whether it's a cat or a dog, right? Because if it's neither of those, it's automatically the last one. So we do all that internally for you. We also initialize the weights randomly, but you can either specify the amplitude and say it's a normal, or what kind of distribution you want, or you can say it's just automatic, in which case it will use this 1 over square root of 6 divided by the number of units in this layer and this layer. Those two affect how big the weight should be in between. Because if you have a lot of units, you want those weights smaller, otherwise it blows it up from noise, right? So it's all good basically. And once you know that you've made an error by over-propagating and comparing with the actual solution, you can then compare your error that you're making for each point. That's called stochastic gradient descent, right? Each point has an error, and that error gets back propagated back. And you want to know how big the error is. Either you compute the error with like a mean squared error or with the cross entropy function. It's just two different ways that we have to figure out how bad is my prediction. You have many classes, you don't really care as much about the mean squared error, you only care about the class that you should have gotten. How bad was I for that one? And that's this negative logarithm there that explodes pretty badly when you're off the 1. As soon as you're not predicting a 1 for that guy, penalty goes up fast. So that's why cross entropy is usually chosen for classification. So once you know how big the error is, you know how big the gradient is at that point, and you can go back, but you just need to know the learning rate. How much should you correct this one weight or bias such that next time you're in a better spot overall for your error function. Now, how much should you move? And in standard neural nets, you have to specify, okay, the learning rate is 10 to the minus 2, then it gets less and less, it's annealing, and then you have momentum as well, and you kind of browse around in this hyperspace, and all these options you have to tune. You have to say my momentum goes up or goes down, my learning rate goes up or goes down, starts at this point, ends at this point. That's already complicated. So what we do is basically, we do this automatically for you, using the ADA-delta approach, which we'll get in a few minutes. But for now, basically, we like to propagate is the chain rule. We all seen that before, so it's all good. Now, what's specific about H2O is that since it's a distributed platform, you have n models, right? In this case, you have like 4 machines, and these 4 machines, I should have a laser pointer to my mouse, let's see, translate into this. So we have machines 1, 2, 3, 4. Machine 1 starts with a model that I call W. And I put that into the key value store, and it sits basically somewhere in this virtual store. And every machine can say, I want that model. So when you go to your web server, web browser, and connect to our server, it's built into the jar file, into the Java code that's executed. You can say, hey, give me this model. No matter on which node you ask this question, that node will get that model and display it to you graphically and show you how it looks like that model. But for purposes of training, you don't care about how it looks right now. It's still initialized at random, right? Thank you. So here we have a random model, put in the KV store. Now we're going down to the next 2 machines with a broadcast. So one node sends it to 2 nodes, and then each of those sends it again to 2 more nodes. So then all 4 nodes have the weights, the neural net model. Then what happens next is that they start training on the data that they have. So if you have 4 nodes, you have 100 gigabytes of data, each node will get 25 gigabytes. Random subset, round robin distribution. And each node will now train on whatever data you want. It could be on the whole data set, in which case everybody will pull 100 gigs, but that might be too expensive if the nodes only have, let's say, 40 gigs. Then you have to say no, do not replicate all the training data everywhere, just keep using what you have. That quarter, that's good enough. And for big data, that typically holds. So you can say, okay, every node trains on its 25%, and after a while, you can specify how long that while is. Your map phase is declared over, and you have now a new set of weights, biases, that are now the new model. But each node has a different model. And you might wonder how these multiple threads here actually train one model. Well, they all racily compete for reads and writes on those weights. So it's actually a race condition that we exploit on purpose to be 30 times faster than having one thread only. So So in case of 32 threads, which is typical nowadays, it's like 2 8-core Xeons or something in the server, you get 32x speed up by just letting those threads go wild basically on the memory. And all they do is read the weights, correct them, and read and write in memory. And the smaller the model, the faster it is because it fits into level 1, level 2 caches. And if you have a huge model, then of course you are competing with read memory access, and all these different threads are having to share the memory bandwidth. And then that's where the GPU comes in handy. So we're thinking about expanding to GPUs as well, of course. But for now, this is basically meant to work on any machine that you have, a laptop, a workstation, a Hadoop cluster. So we are not a particularly specialized shop for GPUs at this point. We have broader applicability. So once all these 4 models are done, as I said, they get combined in the reduction phase. So it's a map reduced. In the reduction phase, what we do is we just average. You could in theory say I score each one, see how good it is in the validation set, and then based on that make my ensemble merge or something. But we don't do that. We don't make an ensemble out of it. We just average. Then we call this the new model. And we never know how good each one was or anything. It's just how we get to our model. The model is what happens when you average those weights. Not the predictions, just the weights. There are no predictions. The predictions only get made with the model that's in the key value store if you were to ask for it at some point. That was one step. We keep repeating those steps. Each step goes over a subset of the whole data, or maybe over 10 times the whole data. You could say train for 50 billion points and then make a reduction, or you can say train for 6 points and make a reduction. It's all to specify it. So yes, there's a paper that says how good this is if you average the models and all, but we've seen it work just fine. So the extra secret sauce that you need to make this work is basically this other delta learning rate that I alluded to earlier. It's automatically picking the learning rate for each neuron, for each weight, each weight between all the neurons. So there's millions of weights, and for each one there's a learning rate that changes over time as a function of the history of how the weight was changed in the past. It's a very good thing. It's like another grad, but it doesn't freeze. It has a chance to come back to life if you want, and it's even better than that. There's regularization built in L1 penalty, L2 penalties. L1 says pick the ones that matter. L2 says, and L1 by the way says pick the ones that matter, and the rest goes to 0. And L2 says give them all a chance, but don't make any of those too big. But also give them a chance, basically. So it balances between similar features. And dropout says just blind yourself out randomly and don't overfit. Just don't see everything as sharp as you want to. Just make it a little blurry. But the blurriness is like a cloud that keeps moving, so it's always a little different. So you never really get too good at learning. You're always kind of sidelined. While that was the intentional race conditions I mentioned earlier, that is also some form of regularization because your weights get screwed up a little bit by the threads competing. It's hard to quantify that, but we've seen it hurt a little bit when you have a tiny data set like iris or prostate. If you have too many threads and they all go wild on a very small neural net model, that hurts because they just override each other in a bad time if you want it. The model itself is a little worse, but not too bad, just a little worse. But for anything bigger than, say, MNIST or something, or even much smaller than MNIST, it's already just no problem. Distributed mode itself is also some kind of generalization, right? Because you have n weights, sets of weights that get averaged. So you're never really able to overfit too much. Then there's also grid search and checkpointing, all the stuff that you want to do, hyperparameter optimization. So this is a detail for those who are interested. You can look at that later. That's basically how you adapt the learning rates. It's just looking at the history of the weight changes, and based on those, it comes up with a new weight. And if the deltas were big in the past, then you keep being big because that means you have to keep changing. But if the deltas, the gradients themselves are huge, then you slow down a little. The delta gets smaller. You don't want to jump too much in the cyberspace of learning rates. So it's all good. This is the dropout idea. You just randomly choose the red axis there, and every time you have a new training point, you just don't see all the input, and some of the features you don't see here that you inside. You can specify the dropout rates for input layer and for each layer in between. Say 10% dropout in input and 20% for each layer, whatever. That was all Jeff Hinton's idea, I think. And that has shown to be very useful. So let's go back to reality now, practice. Let's use this stuff, not just talk about theory. I'm sure you're getting hungry and you want to see something. So let's go to the Higgs boson. Who has heard of the Higgs boson? LHC, CERN, big particle accelerator. $13 billion project, biggest experiment of humankind. So they have a detector that measures something, and you have like numbers coming out, 21 numbers that tell you what happens, so to speak, and you have to decide is it a Higgs or not. And there's a data set you can download that has actually 11 million rows and 29 features, because they added some extra features that are human-made. Some physicists wrote a formula that says this minus this and then square root of that or something that basically helps to compute useful properties in physics lingo, like transverse momentum or something from longitudinal momentum, and you know that the energy conservation helps you or whatever. And with that you can do extra feature engineering based on basically domain knowledge. Okay? And together you would think it's better than having just the low-level features. Right? So there's a paper that came out this summer in Nature that says how we use deep learning to do particle discovery. And they had an AUC. Who does not know what an AUC is? Okay, so that's a number that says how good your classifier is for yes/no classification. If that number is a 1, you got everything right. If it's a 0.5, then you're basically random. So 0.7 means you're somewhat in between total random and being totally right, which is typical numbers basically. So you want to get that number up. And how do you get that number up? Well, by adding these high-level features to the low-level features and coming up with these 80 numbers here. That's the complete feature set, right? So the human insight, this domain knowledge has helped in this case. This was a boosted decision tree. This was a neural network model with one hidden layer, and this is deep learning. That's what the papers are saying, right? They're telling you here, deep learning, hopefully this can be done better. So I tried to reproduce their numbers, and I just ran it on a linear model. It's a 0.6, really bad. Linear is not good enough to tell whether it's a Higgs or not. Random forest 76, random gradient boosted 75, whatever. It's all roughly in the 76 area there. So that's the baseline performance with H2O. Slightly better than what the shorter scientists were using, but they were using something older. I think it's called TMBA, Toolkit for Multivariate Analysis. That's like an old package that they were using since the 80s or so. So that's good. But let's go now to all features. And we also see a boost that they saw. In this case, it goes all the way up to 83, 84 almost. So that's fine, right? Let's see what we can do with deep learning. However, we don't give them these extra features. Deep learning is supposed to make up features, right? So we don't want to help. We just want to give them the low-level features and say, figure it out. I'm a lazy data scientist. I don't care about physics. I just want to do nothing. Click a button and say, make it right. So let's do just that. Here's it's us. Here we go. So this is a cluster that we have in our office in Mountain View. It's a 10-node cluster. You can see here 10. These are the IP addresses, ports at which they can be talked to. They have 256 gigabytes of memory each, but they only gave it 30 gigs each because this is a small data set. I would have gotten away with much less than that, but I just thought that 32 gigs is a good idea. Because maybe you want to do something else than just run the Higgs problem, right? So what I did here, I click on H2O, you see all these links and stuff. That's all nice. But what I did was actually, I ran some jobs in the past. The first job ran at 2 o'clock, and it took 3 seconds. That was a parse job that I imported the X data set. That is 11 million rows, 29 columns. It's about 10 gigabytes on disk. It got compressed into 2.3 gigabytes. Something like that, I believe. Maybe it's a little less on disk, 5 gigs or something. And that file is basically in memory now on those 10 machines. It only took 3 seconds to parse it. It was being parsed in parallel. So that's fine. What I did then is I ran a GLM model. You click on that. Now we're asking the distributed key value store to fetch us this model and display it. This said, this is the formula you need to use to predict whether or not it's a hit. Okay, here are some coefficients. It's this many times this coefficient. Here 0.001 this time. C4s, 13s, 19. They all have a name. How much you use this. That's logistic regression. However, that wasn't that great. So earlier, the AOC curve is very flat. It's basically not much better than a diagonal. The diagonal means it's false positive and true positive rates go the same way. So whatever you do is basically random. You get it right or not, you go up or not, you go right or not. Going up means you get it right, going to the right means you get it wrong, right? And you do just zigzag thing. One time you get it right, one time you get it wrong. You make a diagonal. So you want to go up more than go to the right, because up is true positive. So here's your confusion matrix. You can move your mouse over those points and you see how this stuff changes the confusion matrix. You can ask where would I have my best per class error, where both classes are as good as it gets. That would be in the middle somewhere. There's all these little helper things that we have. You can choose a threshold. You can say as soon as the probability is 0.9, I declare it a Higgs, otherwise it's not a Higgs. Where would I end up? And you would get this confusion matrix. You would say everything is false, basically nothing is a Higgs, except for maybe 38 things that you say are above 0.9, but that would not lead to a very good confusion matrix. You get basically a half wrong. Anyway, this is all just insights into the model. So I did run another model that was a GBM, the random forest. For example, the GBM that was 50 trees, and this is much better, right? But this is the training error. This is not the validation error. This is not the training error. By the way, if you set this HTML here to Java, you'll actually see the same model, this time in Java language, exported for you to take into your Storm class production system. This is the whole source code for this model, including the entire tree logic. This will say, is my coefficient 7 bigger than this number? If so, go down the tree. And in the end, you get a number out. There's no heap allocation at all. This is all in the registers of the C tree. So this is nanosecond scoring time for each tree. It cannot get faster than this, right? No Fortran code can be fast. This is x86 instructions just going down. Anyway, while we're at it, you might as well type JSON here. This is what the web browser or your curl script can see from some other client. There's a bunch of stuff that you don't need to know, but it works like that in the background. It's basically just a REST system. Okay. All right, so now let's run a deep learning model. So if you really want to do, and I of course have a link for that because it's just a REST call. The link says query my deep learning API and set the source, the training data set to part 0. I did split up the data set into 3 pieces. First 10 million and then 500K, 500K. 10 million is for training and 500K for validation during training, just for fun. And then the last piece can be used later once the models are all built to see how good the models are for test time. So in this case, I ignore the last 7 features, because those are the human-made features. I say here's a validation frame, just for fun, and everything else is like standard rectifier is our default, active estimation function. Rectifier means it's just a straight line, easy to compute. The gradient is 0 if you have a negative value, which means a lot of the back propagation can be skipped. You don't need a GPU to be fast in this case, you just need to not do the math, because if it's 0, there's nothing to back propagate. So you can do shortcuts like that also as well, which speeds up stuff a lot. So here we have a grid search going on with two different hidden layer architectures, either 4 times 100 neurons or 6 times 200 neurons. This is one option of doing grid search. You can specify multiple values pretty much everywhere where you can specify a number, and it will make a superset of all these cross products. It can blow up exponentially the number of models it will build it. But that's often useful to get an idea of what's happening. So I say submit, and now there's 2 models being built. One with these architectures here, and one with this, right? 6 and 4 later. And at the end you'll see, it's scrolling fast enough for it refreshes. So here, there's the model key, and there's an error, and that will get better. So if I click on it, I will see this model being updated as we speak. Here's the 4 layers of rectifiers. You see the rates as they are right now. And you see an AUC curve of 65 on the holdout set here as was used for validation during training. The AUC is the area under the curve, and the ROC is the Zebra operation curve. So it's the curve itself. So this is not yet that great, so I do a reload, and it's going to be better, because every time I reload it, I ask the system, hey, what's the last version of this model, and it got updated because we did a lot of those MapReduce passes, right? So already it's up to 76. This is as good as a random forest model ever going to get, right? And this is just trained in the last 40 seconds. And this is running on the clusters. If I go to the perf bars, that's our 10-node cluster, and that's the CPU usage. So they're all, right now they're communicating, and now they're busy computing. And I specified time in between to be automatic. In this case, it's doing this every few seconds, as you can see, synchronization between the different nodes. So for those who are hardcore HPC guys, you would say Rise is blue error, right? It should be asynchronous and should be like super fast and all that. Sure, you can optimize a little more, but then you don't get this nice behavior where you have these atomic updates where you know what's happening, where you can store it, where you can save it. So it's usually not worth to pay the price. Somebody who operates a loop cluster is not worried that their machines are idle. There's enough jobs running at the same time, but this is usually always full. Anyway, so this is running now. We can look at the job status. The grid search is going on. The first model is almost done. We'll get back to it in a few minutes. Okay? Let's go back to the presentation. So in the meantime, MNIST, of course, is the standard. Don't listen to anybody who says they know what they're doing that doesn't show you the results for MNIST or ImageNet. So everybody here is doing the right thing at this conference, I see. So since we don't have convolutional layers yet, I'm restricted to the MNIST data set, which is not bad because at least it's well researched, and we know that without convolutions, the growth rate is 0.83%. That's the Microsoft Deep Convex Net. So no distortions, just 60,000 training points, and then test on the 10,000. And we also got 0.83 on the 10-node cluster that you just see running. This is command here in R. So this is basically saying install the R package from CRAN, load the R package into R memory, and all that package does is know how to connect to the 10-node server. It doesn't run actually anything in R. There's no math being done in R. R is not distributed. So what we do is we say connect to the 10-node cluster, and then we say load the data into the 10-node cluster, distribute it, and then run deep learning, and then tell me when it's done, basically, and tell me how good you work. So this is now saying run this model with 3 hidden layers, use the rectifier with dropout, run for 8,000 passes over the data set. The data set is rather small, so you can do this in a few hours. I think it's 10 hours as well. Do a little bit of L1 penalty. Not all the pixels are important. Pick the ones that matter. dropout makes it like such that you don't look at every single pixel and say, oh, this has to be there, or otherwise it's not a 5, right? Obviously it makes sense to drop some of that stuff randomly. And the classification stop p -1 says don't stop once you hit 0% training error, because I can keep generalizing and improving my generalization even though I get all the training samples right. I still keep getting a better model because I keep regularizing with the dropout. So I smoothen the hyperparameter space, and what I'm looking at is basically well, I don't look at anything, right? After 10 hours I stop the whole thing and I say, let's see how good we are. Then I basically have a model predicted, and then I can score. In this case, I just ask what's the future matrix at the end, and that's built on the validation set because we gave it a validation set, but it's not being used for training. And there's a link to the actual notebook that we have that explains all this. We have like dozens of use cases on this learn.h2o.ai website. Yes?
Where's the X and Y?
X is the predictors, Y is the response. So 784 is actually 28 squared. That's the number of pixels on an imaged raw image. And they're all just black and white values from 0 to 255. This is what you saw earlier, this Java model. You can also click on this Java box there. It's like some models are so big that they don't show everything in the browser, so you have to type Java and pay a license to us if you want to put it into production. So this scales. Obviously, as you saw earlier, right, all the nodes are busy processing their data using the maps. And I would ask, how well does it scale? Well, as long as they're busy, it's perfect. Once they communicate, that cuts down the scalability, right? Because every bit of communication hurts. So unless you have InfiniBand or super light speed wormhole or something, there will be some time wasted communicating. So people have 10 gigabit, maybe 1 gigabit or 100 megabit switches over something that's not good for this stuff. So you want a fast network, or you just wait a little longer. And usually people just say, oh, we only have a 1 gigabit network, but as long as it runs on fine. Right? So my HPC background has to suffer a little bit when I see these production clusters sometimes, but at least I know it's meant to work. The real question is how good is the accuracy after you give it more nodes, give it the same time of training or 10 times less time of training or something like that. And that would seem to be pretty good, but it's of course not like linear. It's not. If you have 10 times as many machines, you won't get the same number in a tenth of the time. Maybe you need 1/5 of the time or a third of the time or something. So it's not super. It's not linear. Let's say in the reduction of time it takes to get to the same number. But that could depend on the problem. I haven't done too many studies actually on this, so it really depends whether the regularization that you're getting is coming from your model itself or from this averaging between models or whatever it is. So there's a lot of things that play into each other. And in the end, it's not about the training error, but the validation error. This was basically something with 8,000 columns, all text-based, yes or no, bag of words. Was this word in this description by the user or not? It was trying to sell something. If it says vintage 18 karat gold watch, then these words are enabled, the indicator functions. And now you can predict is it a gold watch or a silver watch or something like that. There's 467 output classes. And a random forest would suffer greatly with this because it has to make a lot of trees that says is it yes or no for Rolex, yes or no for silver watch, yes or no, or isn't this? So that will not be easy to do with a regular logistic regression or something as well. So we got 11% test set error out of 143 classes, basically out of the box with these parameters there. That was just the same parameters about that was good for MDs. State dropout. Who knows whether dropout is the right thing in this case? Save L1. Same hit and dropout ratios. The only thing that's different is the output layer is not 2,000, only 1,000. But I don't know what's the best thing here. But this basically gave you a hit ratio of 90% for the top one spot, right? And then 96 or so for top 5. So that's not bad if you want a system that just tells you what it is for multi-class classification. There's an anomaly that you can do with unsupervised learning. Right? You can learn the structure of MList, and then you give it another test point and say, does this match the structure of MList? And if the structure of MList says, no, you don't look similar, then you're an outlier. So now the question is, how do you figure out what's the structure of MList? I gave it away, it's an autoencoder. An autoencoder says, make a neural net, but instead of predicting a 1 or a 0 at the end, you predict yourself. You have 784 output classes if you want, output numbers, and those have to match your input numbers. But you're not just doing identity mapping, you're going through a thinner network. In the middle you only have like 50 neurons. So my 700 neurons get compressed to 50, and then they are told to learn how to make up somehow this compression, how they can learn the most they can, such that they can cover the 780 somehow, right? And you can say this compression is exactly what you want. That's what machine learning is all about. It's all about data compression. In this case, you're trying to learn the structure of the data with as few points as I'm giving you. For example, 50 neurons in this case. I'm doing 10H neurons because 10H is a little softer than a rectifier. Since I only have so few, maybe even a little smarter neurons. Only trained for one epoch. Actually, why don't we do this live? I think we can do this off here. So I have this latest stable version 2832 downloaded, the zip file unzipped, and I added to the directory. And I do this twice, just for fun. We can do this in a multi-node configuration, even on the laptop. So I'm going to run java-jar, H2O.jar. And I do this twice. So now it says cloud size 1. Now I do another one. Then it says cloud size 2. The order is covered. Right? This would happen if you have multiple machines that do multicast, then it's covered jar. If your IT guy says don't do multicast on your Hadoop cluster, then you can give a flat file with the IP addresses and port numbers. So it's all good. Or even launch it from Yarn or Mesos or MapReduce, whatever. You can launch this stuff with a one-liner where even the jar gets distributed by the mapper, by the Hadoop launch system. Anyway, now that we have this, it says we can talk to it from our local host. So let me go to here. This is now localhost. This should show me 2 nodes. Here, both on the same IP address, that's me. And they all each got 4 gigs. The default is a quarter of the system memory. I have 16 gigs here, so now I'm getting 8 gigs together. Now I'm trying to go to R. I have this anomaly detection tab. The slides have a link to this file. It's in GitHub, and the file itself is actually also a markdown file, which you can look at as an app, right? Basically as a displayable markdown file. But it's also an R script, because all the comments are like in the right places and stuff, so that you can actually execute this script. So I'm going to press run. As it runs, I'll show you the code. It's the same thing earlier. Load the data, connect to the server first, load the data, set the predictors to the response, remove the response because you don't care about what the digit is, you just want to learn the structure. Then we run this autoencoder, same thing that we saw on the slides earlier. Basically learns the structure in one pass over data. So it's not that great, but it's good enough to make a point. Then I'm computing the reconstruction error with the anomaly app. It just says give me a test set of the model. Oh, here you see stuff coming out. So let's go back a bit. These were the reconstructions that are the easiest to reconstruct. So at the bottom I say, show me the top 25 reconstructions and show me the actual image basically of the reconstruction. So these are the easiest points to to match to the data structure belief that I form. Right? So my system learned what is a list, and I give it the training data to train, and then I give it the test set and say, does this match the training data? Now, arguably, the training data is also ugly. There's ugly digits in there. But if something's ugly in the test set, it's most likely not like something else that's ugly in the training set. You could say everything that's ugly is kind of out there, an outlier land. So there's a chance that the good stuff overlaps. So this is the good stuff. Top 25 reconstruction errors, the smallest reconstruction errors. This is the actual creation of the training data. Now these are the middle ones. I call it the good, the bad, and the ugly, right? This is the bad. So these are, you can interpret them, it makes sense, they're reasonable. And now we go to the ugly ones. They're starting to get ugly, you can't even tell what they are. And that's because the training data was bad, right? This is the end this data set. So it's not easy to get to this 0.8% error of the test set if you have such digits in there, right? And you're not allowed to rotate. So this 6 here down there, without rotations, there's no way you're going to learn this properly. Or this 2 here, if it's even a 2. Alright, so that's that. I hope you saw that that was that. So I can just kill it here. Actually, before we kill it, you go look here in the job, so you can see that I ran. As far as the training, the test, I looked at the learning model. It was an anomaly model, like an autoencoder. Then I ran the anomaly app, and then I got the deep features out. Similarly to the last presentation, so you can also get into the deep learning layer and extract the features. So now I can, you can look at like all kinds of stuff here, right? You can look at the log file or whatever. This is all debugger stuff, but I'm going to just shut this down. And now you see that here, most of this process got killed. Much for my local cloud. Now let's see what the other guys are doing. Oh, it's done. This was a 10-node cluster, so it should be done. Whenever we get back to it, it'll be ready. Oh, perfect timing. So we want to know how well did deep learning do now for this Higgs problem, right? On the validation set, not on the training data. So when we go here, we can see these two models. Just click on this guy and say, okay, this is my 6 layer network. And it has a number down there. 78.5. Okay, I've seen better, I've seen 79.9. So this is showing you that there's a little bit of fluctuation in the, every time you run it, it's slightly different, right? Because it's multi-threaded, there's race conditions, and there's also a seed. Run it, that's how you initialize. So deep learning is not reproducible unless you set the reproducible flag, in which case I run single-threaded. Single-threaded and deep learning, they don't go well together, right? It's too slow. So you don't know what the model means anyway. It's a black box, so what's the point? You can ask for feature importances. Just like random forest, there is a big variable importance based on the weights and their propagation. Big weight going in, and then another big weight, then it means that this means that somehow this feature from the beginning here there was kind of important, right? So there's a way to compute feature importance, and we have that in there as well. Just like for every method we have. So you want to look at the actual model comparison. There's a multi-modal scoring, which says compare models. Here, deep learning model, GBM, GLM, random forest, compare all of them, score them on the last print, 500 points, and it's doing that right now. And then you will see a model comparison here between the models. Of course, this is a small website. My browser is small, but you can see that deep learning has pretty good AOC curves. You can also plot them here, or you can plot them as a training time versus AOC, for example. You get some plot at the highest point, I hope deep learning. This here would be the slowest one. but reasonably good. Random forest is a little bit better, but it needs less time and so on. So you can study all this stuff. You can run hundreds of models and you can see which one makes sense. However, this 0.8 is not that great, right? You would say 76 all the way to 0.8, that's it. Well, it was just a few minutes here, right? This was last time, 266 seconds. We got a 0.8 last time. This is basically what you get with a crappy model of 200 neurons, 6 layers. It's not that bad. If you run it longer, maybe it gets up to 83 or something. We got actually to 87.1 there with a 5-layer neural net. The paper that was using Piano got to 88. So no doubt if you have a GPU and you have a half year to make a publication and you have a dedicated group and this, that's the only aim is to get the highest number, you can get a little higher, right? But this was basically 5 times 500 and one L1, L2 number, go, 8, 10 hours or whatever, 5 hours, and you get this number. So it's pretty easy to get your numbers. And there's no tuning in the Java code for a Higgs problem. Right? Obviously, we run many problems. PayPal is running this in production for a fraud detection. They don't have Higgs data, so it's just basically that's what deep learning does, but not H2O or Piano. It's just the strength of the method is that it picks up these features. All right. So what's coming next is H2O Dev, which is the developer-friendly version of H2O, which will have a Python API, which will have a Flow user interface here. Let me show you how that looks in reality. So we killed the old school Java version, and now we bring it to my environment here. This is our code base. Here you see a partial sum in the back propagation or forward propagation, all kinds of logic. But anyway, I will run this H2O Dev, the new version, and I will go into the Flow API. Reload here. This should now respond, yes. So this is my local host responding to me to the new user interface. This looks similar like IPython. There's fields and cells and stuff, and I could now type, like, I don't know what to do, like assist or something, I believe, Control Enter, and it tells me what I can do. I can import a file. I can say, okay, maybe small data, maybe airlines, and then I say load this file here, import, okay, parse it now, show me how it looks like, yeah, makes sense, otherwise I can change some things, parse, let's see how this is going, oh, already done, when we look at it, these are the labels of the columns, there's a summary, I can say, okay, let me see, let's say, departure time maybe. Show me a distribution of the departure time. All kinds of stuff is going to happen here. But for now, I just refresh the page, delete it all, and load a prior flow that I made earlier today, 3 hours ago. And I can say, okay, run this. But I can see it makes a random frame with 10,000 rows, 100 columns, with some integers, with some binary columns, with some categoricals, with a response that has 2 factor levels, like yes, no, for example. I want to look at column number 6, how is it distributed, more or less uniform, that's what this random generation is done. I can say build me a GBM. And you see I can use the mouse and I can use the cell. So this is like a hybrid between a GUI and a flow-based IPython. It's more than just a scripting language. It's also a graphical user interface. It combines everything. It's basically talking via this REST API, which is self-declared. It says, oh, you asked for frames, so let me tell you what I have for frames, right? And so on. So the same thing for deep learning, of course, I can run this. And as it's running, I can say, okay, make a prediction with the GPM model and with the deep learning model that's in the middle of building, and already made a prediction. This was a 0.90 AUC. Now I can do this again. It's probably going to be slightly different because it kept training some more, and I got worse again. but it's just fluctuating. Of course, this is all random data, so it doesn't mean just train the random data. But you can see that this is the future of H2O. Right? Flow-based, it also has a Python API. So let's look at the Python API. While this instance is running, I can go to H2O ref, H2O pi, and in here there's some scripts. This is all brand new. And this is like a prostate example. It says connect to the cluster, load this prostate file as a frame in H2O. This, of course, would be a 300 gigabyte file from HDFS. This doesn't have to be small. I just did a little demo here. Delete the column called ID, turn the capsule into a factor, make all the numbers volume 0 into missing values, then split the data with 80/20 randomly, and run deep learning with those parameters. And this, when I execute this, will run something that actually ran in this Java instance, right? And I will be able to go to the Flow API and say, help, I don't know how to find a model. Okay, here, get models, and I should see the learning model. This was the one that we just read on the prostate. So all of this is interacting from different points of view. Of course, you can run your own Java code also. We have Django and tests and all that stuff. All right, so this is coming up. This was again the Python example. There's a link in the title there. If you go there, you can see what we're doing. And now it's up to you. So I hope you have a little bit of time left for you guys to run something. So we'll first do the web user interface-based approach with the old interface, not the new one. The new one is coming out in a few weeks or months. But we'll use the old one, production-ready, stable API. And we'll import the Higgs data set, we'll split it up, we'll run some grid search, we'll pick the best model, and keep training that one for a little longer, and then we look at the scoring results. Okay? And then the second half will be RStudio, for those who have RStudio installed. Who is that? Somebody has it? Okay, good. So whoever likes R, I mean, I'm not forcing you to learn R. If you know Python, just read the techniques, and you can use this for Python. But R has been really dominant in the data science community, not in the computer science, but more in the data science. So we'll run different things from R. And there's also, I think, more we have links to all the other stuff we did at H2O World. A few months ago, we had a conference where we showed all the use cases, a lot of examples. So if you have your Docker environment going, you should do a /run H2O, and it will launch you an H2O instance at that IP address that move to Docker IP tells you. It might be localhost, but if that doesn't respond, then you choose that IP address. Not mine, of course, but the one that you get. And then you can go to that URL. So in my case, it will be 1 of 3.
We're not using Docker when I just run it local.
Yes. Localhost :54321. But now you need the data. And if you don't know where the data is, you can look at the following file in Jetpack H2O. There is a Docker file, and it says download first the H2O tarball, a zip file, I should say. That's actually what you need. That's the jar that I launched earlier by hand. First 3 lines. Then the next W gets, those are the data sets. So if you have this file somewhere, that will help you. If you don't have it, then I'm sorry, you have to type this in. Get those files to wherever your H2O is. So if you have a Docker image, those files will be next to the H2O jar. If you don't have it, then you have to basically do this in your local scratch directory. So wait a little bit for you to please get an idea. You don't need to download everything, you can just download one file or so. I'm also moving the image data sets to the name. You don't have to just specify the other name. this was meant to be in the background. Done automatically by Docker during the build process. Or if you want to play with H2O Dev, the new version, then you go to our GitHub repository. So just go to GitHub and search for H2O, and you should find H2O-dev. If you don't find it, then go to H2O.ai. And it's also a jar file. You can also do Java as jar, and the jar file you also go to local host 503 and so on. It's all the same.
What sort of performance gain you might get?
So the question is, how much performance gain can you expect via GPUs? Depends on your access there, right? If you have, if I basically write CUDA code on a distributed GPU cluster that's really fast CUDA parts, and somehow I expose that. I write a lot of CUDA code around everything, and then at the very end it tells me, here H2O, here's the model or something, now you can use it for prediction time. Then of course that's super fast, right? But that wouldn't be H2O running, right? So sure we can hook it this way, but if you say the Java code has to tell the GPU what to do, data in and out all the time, you use something like OpenCL or JNI or whatever, I am a little bit unsure at this point how fast this can get, because you do have the data movement. And if you have, of course you can stream the data slowly, and the GPU has lots of work to do, especially if you have the motion layers. So I'm not too worried about the data movement for training data, but it's the model that has to be communicated as well. There's some overhead with that. So once you go to distributed systems, there's always the network aspect, which will always be the same, no matter how fast you train in between. But that's when the network might start to dominate your overall time. Right? That's why companies like Baidu, some press release, they're using InfiniBand networks to get their latency down, bandwidth down. So if you just have a 1 gigabit Hadoop cluster, and you have super good GPUs in there, it's kind of pointless, right? Unless you run n different models, each one a different model, and do this grid search. But this would be a tailored solution for a kind of a misfit cluster. So I don't know what the value is of that. So are you okay with this? Like who has Docker running and has access to the cluster on their machine for a web service? Only a few. We're still trying to download H2O. All of this is also on our website, learn.h2o.ai. It was our training day. Click on read, and there's an explanation for pretty much everything. So there's supervised learning, unsupervised learning, the anomaly detection app that I showed you. There's dimensionality reduction, gains, clustering. There is a random forest gradient boosted trees. There's a whole deep learning section also on the MLIS data set with grid search, with random search, set at higher dimensions to not have a human given strict grid, but to have like random search, and then you get more lucky basically as soon as you have Monte Carlo samples versus orthogonal cross products of hand-picked values. You can do all kinds of stuff. Checkpointing, then again the parameters for the wrong record number, cross-validation, variable importances, adaptive learning rate. Then there's a bunch of tricks and tips at the bottom, so there's plenty of material also in this booklet. And there's an advanced chapter. The advanced chapter has multi-modal parameter optimization for the Higgs problem. So we have lots of code here to fit GLM, the random forest, QVM and deep learning, compare all of them, do cross-validation, do grid search. In the end, you get a leaderboard that says which model is the best, with what feature importances, how long it take to train. So this is all hard code, right? But it's all there. So if you feel like you need more inputs because you don't know what to do, it should be all there. There's feature engineering. There's that's what the adult data set, log transforms, this kind of stuff. Then there's one other cool feature that's called interaction features. So if you have categorical factors like cat, dog, mouse, and another one that says employed, unemployed, part-time or something, you can do the cross product as a tool. Then you have cat, employed, cat, unemployed, and so on. And that will be a new feature, right? And instead of doing this in the model implicitly, you can explicitly make those combinational features and then have a new data set that has all these interactions in it. And then you can run a GLM, for example, logistic regression, and then see, oh, this feature matters, this interaction is important. And you can also do this in like any order. You can have 5 fifth order interactions, all different features interacting with each other. You can have this on itself. You can have a factor level with 70,000 zip codes, and you can say, only show me the top 100 zip codes that happen the most frequently. This might not be correlated with the response, right? Maybe the one in Atherton is really the ones that are rich and not the most common ones, but this is like a way to chop it off and say only keep the most important factor levels. So you can say instead of 70,000, I only want 50. And then your data set becomes smaller because deep learning will expand those 70,000 into 70,000 input neurons. That will be expensive because the first weight matrix will be huge. So this is one way to deal with that. All right, so let's go back to what we said we were going to do. So whoever cannot do this, I apologize. That's why I made it super easy, right? You cannot get any easier than this. So you basically have an H2O cluster. Click on import, type the dataset name. Could be HDFS : / something, or S3, or just a file in NFS or on your local disk. You say import that file, and then you say, okay, I want this to be parsed. That's currently how it works in the old version of H2O. So let's do this. I'll do this now on my Docker image. So this is this guy here at this port. I'll say data, import. And there should be a X data set sitting there, right next to the zip file. That was shipped with the Docker image. Say submit. Click on the file. There could be multiple files because you gave a whole list of like you can also do a regex basically, and you can choose all kinds of stuff that matches a certain pattern. Then you say submit because it's all default. It's all good. This will now parse the X data set. And by the way, if you go to the water meter, you will see this little system has 8 cores in my case. It has idle, right? That's my laptop's performance bar. Okay, so we have 100,000 rows of the X data set. That's a small sample that I shipped with the image. So who has this? There's only a few people. Okay, well, the rest can just imagine it and runs. It's not going to be different because it's the same bits, identical copy of everything. So now I say what? I say click on deep learn. Now split frame. Split frame. You want to split the frame. Okay, fine. Split it. 75 is. You need to specify one number to split it into 2 pieces, right? If you gave 4 different numbers, it would split into 5 pieces. You just have to give the points at which you cut. So 75 means 75,000 and 25,000. Now I can click on part 0 and use this frame. And I can do all kinds of stuff. There's some links that we made. Not all the things are linked to, I guess, but most of the useful ones. So in this case, I want to run deep learning. So let's confirm that with our instructions. Yes, so we split it. We point at the big piece and we say to deep learning. The big piece is our training set. Whatever you click here on deep learning on, that's the basis for deep learning. That's the training data that gets auto-populated. It's just a little link that we make for you. So the response will be the first column. Now you could ignore the last 7 if you wanted, but you don't have to. I will not do that for now. But I will do some grid search. Now what grid search do we want to do? Let's see. I said choose a response. I said, validation set fine. Because we split, why not use it, right? X part 1. So now we have part 1 in here. Then I say make 2 different topologies and put in 5 epochs, for example, and 2 different row values. But you can choose other values if you want. So for fun, I will do 20, 20, 20, and maybe 45, 55, 94. And I do this for 5.34, whatever, it doesn't matter, epochs. And I will train this many points per map phase. And I will have the adaptive learning rate. If I don't have adaptive learning rate, then I'm stuck with giving rate annealing, a rate decay if I want between the different layers. I can have different starting values of learning rates. I have a momentum start, a ramp, a stable value of momentum, and whether or not I'm on nested off accelerated gradient. So this is a lot of extra work I need to do. But adaptive just works usually. I've not seen it not work. So that's fine. Let's do 2 different epsilons. I mean, you can do a row epsilon or whatever. You can also enable the expert mode up here. Once you do that, you have a lot of more features that you can unlock. You can say how often you want to score, how many points of the training data you want to use as scoring points. Because if you give me 100 gigabytes of training data, I'm not going to score on that every time I score. I don't need to give you a 12-digit accuracy on the training layer, right? And you just want to see a rough idea of what's happening. So it automatically subsamples to 10,000. You can change that. You can say how much of the total time you want to spend in scoring. You can score less frequently. You can say whether to stop once it hits this training error. You can say whether you should balance the classes. If you have buyer or no buyer, or churn or no churn, and it's like 1 in 1,000, you can upsample the one and bring it up to 1,000, so to speak, and it's 50-50 again. Or you can change this balance. You can specify I want it 5 to 1 instead of 1,000 to 1. You can specify those upsampling factors for each class here. You can say after you upsample by this much, and this whole thing becomes too big compared to the original data set, scale it back down. So there's all kinds of knobs that you have. They're all explained in the booklet, so this should help you get going. This is another important one. Replicate training data. The default is yes, which means the MNIST data is not cut up into 10 nodes, for example. Every node gets all the MNIST data because it's small. Typically, users have smaller data than their nodes are big. On Hadoop cluster, they have 64 gigs or something. Most data sets are maybe a few gigs, right? So it's okay to copy all the data everywhere in the beginning and then run for the next 5 hours. You get a better model that way. So the default is to replicate. Now, if you do have 300 gigabytes, you should turn that off. Otherwise, it has to send it anywhere. And this is the reproducible flag, which you don't want to use unless you're benchmarking or like making sure that the stuff is correct. But I would be surprised if you found a bug because we test a lot. But if you do find something, that would be great. I would love to see that, especially for like max out. I don't trust max out myself as much. The 10H or the rectifier I will use, but the max out I don't use as much. So a little bit caution there. Also the stuff that says experimental is usually experimental. There's a feature hashing trick. You have zip codes, 70,000, you can compress it down to like 500, for example. And then there's some feature hashing to get down to 500. Some of these features are experimental, but they're also only in the expert mode. So if you don't know what expert means, then you don't need to know, basically. All right, submit, and now this will run. This grid search, and at the end you see, oops, again, faster, here we go. Different models, you should see something similar. So now I can click on the best one on top, See here, this model had the best AOC of 78, which is on the holdout. So similar to what we saw on the 10-node cluster earlier, just like here on my laptop. Of course, this is on 100K ROMs, not on 10 million. So this might be crappy data. Who knows, right? It's hard to compare exact numbers if you have a small subsample. But still, this is nice. See how it got better in a few seconds. And now I said here, after we do this, you're supposed to pick the best one and say continue training. And then do 20 more epochs. Okay, so I'll do that. I'll go up to this model, say continue training, because there's a link for that as well. That auto-populates, again, the same training data, and it has a checkpoint. So the model now becomes its own checkpoint, and it continues training itself for 10 epochs. But I say I'll make it 20. Make it whatever, 19 point something. There you go. And you can also change how often, how many points are it per map. So if you say, I ran for the last 6 hours doing big maps so that there's less communication. But now I want to fine-tune the convergence, you can reduce that number and make it communicate more often. So that's why a checkpoint is useful. You can just stop it. You can also turn on L1 penalty after 6 hours and say, now I want to have some penalty because I don't trust that this model is the best. It must be better because training error is this and validation error is this, right? You can bring it closer. Anyway, that's how you do this. It's also super easy. So I will keep training some more. Let's see that it gets up 78.7. Get up a little bit, 79. So yeah, it seems like it's helping a little bit. So that's that. That's basically the user interface. You can look at it. You can just click on this threshold again to see. Like in this case, it was 44% wrong for non-Higgs and 50% for Higgs because we said F1 is what matters. F1 says, how well can I find the Higgs basically? But I say, no, I don't care about Higgs. I want to find both like equally well, right? So maximum class errors are minimized. I want both classes to be as good as possible. Now I'm both 28% wrong. So my operating point should be at a threshold of 0.53. Once it's above 0.53, I can set the Higgs. Then I will make fewer mistakes for the non-Higgs. But that's all just machine learning lingo. You'll know what that means if you need to know. Same with the multi-modal scoring. You can go to score multi-modal here, and you should see models, all the stuff I built. You can say compare, score them on this validation data set, and you'll get the comparison here. They're all kind of similar, I would guess. So let's see. Advanced, yeah, all these curves are on top of each other, so not much change. You could ask, what's my AUC versus test time? I wonder where that is. Scoring time here. Now this is not the nanosecond scoring that you get if you export the Java code to your Storm system. This is just the time it took on this cloud, right? That's the in-heap version. However, for deep learning, the Java model that you export is also doing heap allocation. You're not going to store 50 million numbers in a register, right? Iterate. So you have to allocate some numbers somewhere. So just to be complete, if I went back to this guy and I asked to see this model here, I can click on Java model and it will also be there. So this is the deep learning model exported as a Java code that you can take anywhere. It's simple sort of propagation. And of course, all the numbers are appended at the bottom here. For the next 10 minutes, I can scroll. But these are chopped up into little pieces such that the Java compiler doesn't choke. Okay. So now we do the same from R. There's a URL here called IDCC H2O Next.ML. If you go there, so click on this guy or type it in, you'll get an R script. That R script you can copy into your RStudio, into a blank page in RStudio. And then you can just run it. Basically, like an iPhone notebook, you can just run the R script. And you can also do Control Enter for each line. There's no cells, but there's lines. And there's more information again at these places. So there's Git books, there's PDF versions of all these books. There's also one for R, there's one for GBM, there's one for GLM. There's more copies in the back of the R version. So for those R hackers, how you convert a data frame to an H2O frame and back, how you do some feature engineering, what functions are supported, how you run different models, how you make predictions, how you sample, how you check the cluster status, how you upload data, how you install it, how you launch it in a loop. It's also in this book. So anybody is able to do this? I hope so.
I knocked out the response today.
Oh, really? Oh, turn it off. So github.com, then you type H2O. So github.com H2O AI / H2O. And once you get here, it should get easier. I don't know how to make this font size bigger. I had a lot of effort. I have to go to the system settings and then screw up my desktop. So github.com / H2O AI / H2O. Then R. Then examples. And then you click on something with next. Yes. So this guy is a script, an R script. So you can click on raw here. And then you can plain text that you just can control it, or Command A, Command C, paste that into your RStudio. So this is the full path with a raw file, but you can just go through it a second. So R examples, and then H2O debugger Next.ML. So I leave it up there while I open it in my RStudio. Here. Let me remove this other stuff here. So what you need to do now is download this R version of our H2O. And then is the package that gets installed on your system such that you have this H2O R library. And that might take too long even with slow Wi-Fi. So I'm gonna, as long as you have this script, you can do it at any time later as well. But I'm going to run this. These three already ran earlier. Now I'm going to just say load H2O init, which means connect to this cluster. That's on my machine. That's called my H2O. That's what I call inside the Docker image. So port 8996. IP might be localhost or whatever boot to Docker IP prints out. So in my case, I had to do this replacement of localhost. Localhost wouldn't work for me because I have other virtual machines running in VirtualBox. What I do then is I import the X data, which sits locally, so I don't need to give a path, it's just there. I run a summary on it. And it shows me all the numbers. It's the same as an R summary. It shows me the dimensions, 100,000 times 29. I can do a random uniform vector of numbers between 0 0 and 1, the same length as the X data set, so 100,000 random numbers between 0 and 1. And based on those, I will split it up into train and validation. And this happened on the H2O cloud. That's my one node cloud, which is this Docker H2O thing. So in here I just now, this was an old one. So to be fair to you, I will do Docker PS, Docker kill, delete that guy, and say do another one. Run H2O, make a fresh one. I don't want any pollution in there. And this guy is what I want to use. So it's all empty. And from R, I just connect again. Just say connect to it. And do the stuff again. And as it happens, you can now see that there's a job happening right here in the background. And it also should be built in perf bars a little bit, but it's already done, so there's not much to do here. So now we clean up some temporaries. If you want to know what that means, it's basically going to the store here on the data view column. That's the H2O store. You see there's a bunch of last one values. And that's kind of ugly, but that's our R side effect. In R, when you make these expressions, they get evaluated. There's an object created on the cloud that is the result of that expression. And we just have these temporaries. And we don't have our own reference count or garbage collection in this version. New one should be much better. So in the old version of H2O, from time to time we have to run this H2O RM, which says clean up stuff that matches this pattern. That's a correct you can use. And I said remove everything that smells like last of value. So don't call your frame last of value if you get into trouble. You can call your frame whatever you want using this H2O assign function. So here I said assign this thing and name it this. If I didn't do that, it would also be one of the last values, because it would have been just an R expression that survived. And at the end, I delete everything that sounds like last value, and that's gone too. So I had to basically rescue it and give it a name. That's why I basically had to do this H2O assign, if that makes sense. I could have not deleted everything with last value, and it would have been all fine, but I would have polluted my namespace. So this is the clean way. If you do Kaggle competitions, you better do it this way, otherwise you can run out of memory fast. By the way, did I show the Kaggle? Let me show you. You can see here, there's skip books. Just to mention those, they're also there. So there's links in the slides. And this is Kaggle. So we have a bunch of starter scripts for different Kaggle challenges. Click-through rate, you have the soil, the trade check, text goes on, just like advertising. I don't think we have one for industry neutral, but someone else is using it. So there's enough material out there to do real data science. Sometimes a logistic regression like a vocal rabbit might be just fine. Like you deep learning model, you have 100,000 predictors and they're all good features. So you have to be smart about when you use deep learning. You can't just say deep learning solves everything. In theory, yes, but only if you have unlimited amounts of resources. And there was H2O World as well. You go there and listen to customers using it in production, or listen to Josh Bloch or John Chambers, the guy who wrote S and R, not Cisco. CEO Trevor Hasty gave a presentation of grading boosted trees. We had Kaggle panelists. Top number 1 Kaggler last year, he was there giving us some secrets. Top 7 or 8 was also there. And we of course have all these tutorials that we showed earlier. If anybody wants to program, first of all, this is all open source, right? So you can participate in, you can write the pooling layers and convolutional layers, so I don't have to do it. You can write the GPU support, right, in theory. So this is all one nice pull request that says here's GPU support. But we understand it's not easy sometimes to do all that. That's why we wrote H2O Dev, to make it a lot easier to participate in. Who knows how this will evolve, but there's basically enough work to be done on this project to keep making it awesome and less awful. Sometimes there's hacks that only we know, right? Because it's very easy to program high performance, big data, Hadoop stuff, and then make it user friendly at the same time. There's a balance that has to be found. In our case, we found that as long as the user can use it easily, that's what the priority is. Right? It's fine if we suffer a little bit, as long as you don't have to suffer. So let's go back to the R thing. But otherwise, I'm glad I made it through the slides in time. So whoever wants to run more R stuff, there's code there, right? You can run deep learning with different sets of predictors, only the low-level ones or the high-level ones. And then you run this. I can just copy paste some keys here and say run, and then it will not print to the output. But basically, I'm pretty sure you know what the story is, and thank you for your attention. Yes?
So, are the slides available?
Excuse me?
Your slides? Are you going to make them available? Your slides?
And the slides?
Yeah.
There they are.
Yeah.
Okay. The slides are, again, let's see. They will be on Next.ML at some point. For now, they're here.